Welcome, everyone. Again, my name is Zach Albus. I'm an applications manager with Texas Instruments in our power interface business. And today I'm pleased to talk to you about our latest product announcement that we've released to market, which is our TPS 25772 and 762 Q1 Type-C and USB PD or power delivery product. So I'll refer to this product as 772 or 762 as we go through this presentation. And the goal of today is really to talk through what the product offers and how you can use it in system to design an automotive charger that's leveraging Type-C and power delivery. So just to give kind of an overview of what we'll be discussing, I want to talk a little bit about, what is USB PD and how does it fit into the automotive environment. Want to get into details about the 772 and 762 products that we've recently released in our portfolio. And then we'll talk a bit about how those products are fitting into automotive designs and what the feature set is and how it's leveraged in the context of building a charging solution for automotive. And of course, at the end, we'll wrap up with some available resources that you'll have some direction to and how to access to get started on your own design. So with that, we'll jump right in. So let's talk a little bit about USB Type-C and power delivery. And so what is USB Type-C and power delivery? So USB as a standard is well defined by the USB Implementers Forum and has been for a number of years. And this standard is constantly evolving. When we talk about power delivery, what is advantageous to the kind of solutions we're trying to build is exactly based on the fact that it's standards driven. And this is really important when it comes to having as much interoperability and compatibility as possible in the market as devices are evolving, as requirements around those devices are evolving. And being able to build products that can scale and be as compatible and interoperable both today and going forward is really fundamental about why USB Type-C and power delivery is valuable when we talk about charging in an automotive context. So where can you find USB Type-C and PD today? Really anything that is needing to accept a charge or the products that are built to charge those devices, be it mobile devices, be it power banks. You can really find Type-C and PD across a wide spectrum of products, and that spectrum is widening and increasing on a daily basis as new products are being developed. And that is largely based on that standards approach that is minimizing the waste of various kinds of cables that you might need. This is all standardized on the Type-C connector that you can see represented graphically. The evolution of the interface in USB has led to what is now the standard port you'll find on many devices, which is USB Type-C. This offers maximum flexibility in terms of data rates, in terms of the power delivery across the cable, and really provides scalability across devices both today and as we go into the future. And so why is this important now to talk about USB power delivery in a charging context and in an automotive context? And really that's a function of this standardization, this compatibility that the standard offers. And the fact that when you look at USB Type-C in its initial definition in the 2014 timeframe, what it's really offering support for when it comes to charging is 15-watt charging. And while that's really, I think, was a great advancement at the time from a USB charging specification, devices today are very demanding, and the expectations of users that those devices are charging faster and more reliably is as great as ever. And so with USB power delivery, this specification extends upon that standard Type-C charging at 15 watts. And today the specification actually supports up to 240 watts. And of course, that's dependent on the design and the capabilities of the device, but you can see where that scalability is coming into play in a standardized way that is really enabling support as products are developing going forward. So now specifically when we look at the application of USB Type-C and PD, in an automotive context, there are a number of considerations that come into play here when designing such systems. So I think, we're all familiar with the environment when you're inside the automobile, inside the cabin, and really anywhere that there's a need to interface your device, whether it's simple charging, or maybe there's a data component to that in some use cases. Having that flexibility, having a port close by that is at hand, ready to go, is really important. And so design considerations in cabin have to do with the number of ports, the availability of those ports, whether that's to the driver or to any of the passengers that are in the automobile. The ability for those ports then to provide a certain amount of performance, a certain amount of power and charge capability to those devices. So am I concerned about charging a mobile? Maybe I want to expand upon that and be able to charge a laptop. And so that's an ever-growing use case that we'll see that USB PD is fully supporting. Obviously, cost and size are important. Being able to fit these into very small form factors and keep cost efficient is critical in an automotive sense. And then, of course, we come into compliance. And so having solutions that obviously meet the USB PD specification are super critical. And then being able to meet other compliance factors within the automotive environment are also important considerations. And then lastly here is flexibility. Not all ports located throughout the cabin of the automobile have to operate in the same way. Some may offer higher levels of charge capability. Some may offer data support. Some may offer in the future alt mode support, which we'll talk a little bit about. But these are all flexible configurations that as a developer you want to be able to support with your solution. So now kind of focusing in a little bit more on some of what I mentioned in a broader sense for the considerations, really you can translate that into, okay, as a developer, as a designer, what are challenges that I need to overcome in my automotive design when I'm talking about USB charging? And so there are a few factors that are very fundamental to automotive and the automotive environment that are outlined here and represented visually. One of which is thermal management. So you're in an automotive environment, depending on the geographical region, the temperatures, ambient temperatures can definitely rise. And even though we're talking about in cabin, one of the challenges with thermals has to do then with the form factor we deal with, where, when we talk about charging and we talk about the charge ports as modules, these are quite small in form factor and typically as small as possible to minimize space and weight in the automobile. And what that then also translates to is minimal airflow. And so all of those factors are working together to make thermal behavior, thermal performance a really important aspect of design and challenges to overcome in designing such systems. As mentioned, we also have in an automotive environment, EMI, EMC are very important elements to being able to have a robust solution. And so having a product that is EMC compatible is really critical, and being able to show performance and ability to pass those tests in an automotive environment are key. And then we have really that flexibility of charging capability that you want to deliver, because it is a broad spectrum of products that potentially are plugging in an automotive environment that users are bringing into the cockpit and wanting to plug in for charge. And so with the USB PD specification, this is really giving that broader range of flexibility, be it at a 5-volt level up to 20-volt level across a wide range of power density, that makes charging such products very flexible and again enables that interoperability and compatibility going forward. So let's talk a moment about the 762, 772 products and the features that these devices are bringing into the automotive charging landscape. And so for both of these products, I'll refer to them a bit interchangeably, but the key distinction between the 762 and 772 is really the number of ports that are supported. And so what you see represented graphically here are both the 762, which is our single port product. So this is a fully integrated 65 watt capable buck boost converter that implements USB PD. And you can see kind of the typical footprint illustrated in the graphic. The 772 is the dual port variant of this product. So all the same capabilities in terms of performance, all the same capabilities in terms of the physical footprint, the packaging, etc. The one difference is in the dual port configuration, we offer an interface to control an external buck boost that is the voltage and current supply for the second port. And so all in the case of the 772, all of the control is still happening on our 772 USB PD controller. However, we have two independent voltages, two independent charging ports that are controlled inherently by the design of the product using that external DC-DC. And so integrated into both of these products, as mentioned, 65 watt capable, single port or dual port, offering up to 95% efficiency, a number of features supporting legacy charging, which is your standard type A type physical interface that is supporting up to 15 watt in the BC 1.2 mode. There are other flexible modes that we do support. In addition to the standard just power support we have with the products, what we also offer is smart thermal management. We do have some policy controls we'll talk about that have to do with how we share power between ports, so there's flexibility there. The 762, 772 products are firmware upgradable, so this is a key feature of these products that allow for custom configuration to be loaded, and that configuration can be updated over time to adapt as necessary into a given use case or as requirements evolve without impacting the overall hardware solution inherently. So now as we look at how the 772 and 762 exist within the automotive environment, this represents really a few different typical use cases that you might find where charging is going to be important. So this really represents a model where you have essentially multiple chargers up to one charging port per seat in the cabin, which is going forward, this is more and more the demand in automotive design that needs to be supported. So being able to distribute those ports and manage the port power charging requirements independently becomes vital in a robust design. In addition to the number of ports that you have, each of these ports can potentially represent different requirements. And so in some cases, perhaps it's a charge only, as it's represented here in the back of the vehicle with the rear seats. But then as we look at more capable implementations, we bring into the picture what we call what's referred to as DP alt mode that we will support in the portfolio going forward, where it's not only a charge capable device, but it also would support, for example, mobile connecting over that Type-C port and then displaying the image on the display that may be in the headrest or perhaps at the front of the cockpit up in the head unit, for example. So really the intent of our 772, 762 family is to support these different use cases in the automotive design environment. Now, looking a little bit closer into what those use cases may represent, there are just a few examples of how that looks system-wise that are referenced here. And so just to calibrate, what we have here at the top half of this slide is the 762 that's showing really two instances where we're supporting single port designs. So on the upper left is our single port charge only design. And then on the right, you see charge plus data. And the fundamental difference is in the charge plus data case, the design is supporting a USB host or MCU that's acting as a USB host, where there is a data connection that's taking place over that same Type-C port that is also in parallel getting charge support via our USB PD charge solution, the 762. What you also see represented as a difference here is the way in which our 762 is getting its configuration when it powers up. And so on the left-hand side, you see an EEPROM that's represented in the schematic. And in this case, this EEPROM is carrying the application configuration from the developer and it gets loaded into the device at runtime. On the right-hand side, you see that's missing, and that's because the design is supporting a boot from the MCU, where that image is then transported over I2C directly without requiring the use of the EEPROM. And so this provides some flexibility in how that application configuration is delivered and the overall footprint and design of the solution. And then you can essentially see the mirror of that into a dual port solution where you see 2-port charging support with our 772. And in a similar case, you can see the same design constraints that are there for the single port, with the difference being you have this additional external DC-DC that is supporting the V-bus and I-bus for the port B configuration, again, fully controlled by the 772 in terms of the USB PD protocol. Really bring the features into the automotive environment that are important. We'll talk a little bit more about some of the aspects that are either inherent to the design or that are at the control of the developer and designer for such solutions in the next few slides. And so this slide represents one of the very fundamental requirements that need to be supported when we talk about the automobile and specifically for USB charging. And that has to do with the power supply to the charger coming from the battery and the dynamics that can undergo in an automotive environment. This is one of the fundamental differences in automotive USB PD charging from what you might find, for example, in your notebook PC or in a wall adapter, for example. Because this input voltage can vary under a wide range of conditions and needs to behave robustly, the design of the USB PD controller is really key in order to support these different levels of input voltage that may be seen. And so our wide operating voltage of 5.5 to 18 volts is a key feature of the product that makes it ideal in an automotive environment. And so you might run into a situation where that input voltage can drop well below what's typically thought of as a 12-volt battery voltage in an automobile under a variety of conditions. One represented here is so-called warm crank. Similarly, would be look very similar for a cold crank condition, where the voltage is going to be pulled down well below the typical 12 volts momentarily as the automobile is starting and that battery is under load. We do support operation in this range up to 30 watts. And once the battery voltage is then back in the normal operating condition, we can achieve full 65 watt capability. In addition, on the upper end of this, you have the condition known as load dump, where you might run into a fault condition or a disconnect unexpectedly of the supply of the battery from the harness. And this can cause an inductive spike and result in very high voltages momentarily being seen across the input voltages. And so being able to tolerate those voltages that are going to shoot well above the 12-volt typical VBAT is really vital to a robust automotive design. In order to better manage how the power is delivered, the 762 and 772 are very configurable, as mentioned. And what you see here is a representation of the application configuration possible by way of the graphical user interface that is used to design and develop the requirements and the configuration that is loaded into the 772, 762. And so you can see here, there are a number of thresholds that can be set that will define what is the operating voltage, what is minimum voltage for normal power operation that can be configured in the system. For low power, what does that look like? And then ultimately supporting a graceful shutoff in the case that the battery voltage is dropping below a minimum threshold. All can be configured in the graphical user interface for a particular set of design requirements in the charger application. So all of these controls around how the 772 and 762 are providing charge, whether it's single port, dual port, this is all managed by what we refer to as the Source Power Policy Management, or SPM for short. And the design of the SPM is really integrating all of these different aspects around how the port is configured, and then how that port is operating under a variety of conditions, input voltages, temperatures, etc. And so what you see represented here is a very high-level example of one use case of how our SPM is used and how it can be configured in application for a given charger design. And so what we see here is at the top half of this, we really see two applications of our USB PD charger, both basically targeting similar use cases. So 2-port chargers that are charging a mobile or a laptop, and those devices have varying degrees of power charging expectations. And so in this case, just as an example, we're referencing a smartphone that is an 18-watt load and a notebook that is a 45-watt load. And so with our SPM, you have a number of knobs that you can control in the way that the charger is designed and behaves. One of these is around the total system power. You can define the maximum and the minimum power per port, as well as the power sharing policy that is employed in operation. And so what you see here is a contrast between the assured policy as well as the shared policy, both of which are supported by the 772 and 762. And so in the assured policy case, this is assuring up to 45-watt max on each port. And so in order to achieve that, it's a design that needs to be built for 90 watts. And so that is the physical design, the component selection, thermal considerations, all of those aspects come into play in order to assure that 90-watt solution. In the case of selecting shared policy, now in this case, the same kind of use case can be achieved, but it distributes the power in a little bit different way. It's a bit more dynamic. So in this case, what shared means is when power allocated to one of the ports is not fully consumed, that power can be diverted to the other port as needed. And so what you see here in that same smartphone and notebook example, if only the notebook is plugged in, then it can achieve the full 45 watts as designed. When the smartphone is then plugged in and consuming 18 watts, now the power that is allocated to port A, but not being consumed, so basically 12 watts of power that isn't consumed from the 30-watt minimum, this power is allocated to port B. And ultimately what this means is I can design a 60-watt system. Again, the physical design, the components, the cost, the thermal calculations, all of that built for 60 watts, which can give me a bit more efficient solution, total solution, but still achieve the same typical use case that is shown here. Now, of course, if I need a design to guarantee that I could plug 2 notebooks in and charge at 45 watts on both ports, this is where the assured policy becomes a design requirement. But for a typical use case, this does offer developers some flexibility to choose what makes the most sense for their total design, balancing both the power efficiency as well as the cost and the construction of the charger. So looking a bit at a little bit closer into the thermal aspects, so I mentioned thermal management and monitoring of thermals and how critical that is. You can see here a graphic representation of our reference design that we'll talk about a bit more. I'll point you to some content in a moment, but this is real example of the reference design operating at 60 watts dual port. And you can see there, right, there's going to be some thermal increases due to some of the efficiency loss, just the operation of the system. And one of the capabilities that we build into our SPM, into the overall system configuration, is the ability to monitor temperature via a temperature sensor that is constantly being monitored by the 772 or 762. And then through user configuration, set points can be configured on detecting at a certain trip point has been reached thermally, and then what we call thermal fallback, reducing the power that is delivered on those ports in a managed manner, such that the port continues to operate and continues to operate at a maximum charge level that is compatible with the thermal requirements of the system. And so having this flexibility to configure, customize max power as well as the thermal trip points is really powerful in terms of managing those tight thermal constraints that you will experience, when you're designing a system built for automotive. This slide is showing the point about firmware update and the ability to upgrade the configuration of our device. And so what you see is really that basic system for a single port design. And the idea behind this is once that custom application configuration has been built, it's getting loaded into the device. And that's happening by way, in this configuration, by way of the EEPROM. And so once that configuration has been constructed, it gets loaded into the EEPROM, and now the system is in production. And so that's kind of the typical production flow. However, we do support the use case where this could be updated in a field application as well. And so that's really what's represented here. And so in order to do that, I basically need to connect my host that's going to provide that payload to download into the device. At that point, I can, through hardware configuration, I can have a switch, a button that is enabling the firmware update mode. And so that's represented here. So when this button is depressed, this is going to configure this device to enter into that mode. And then we power up the system. And when that happens, the 772, 762 will enter into firmware update mode. And at that point, the button can be released. And now the device is able to accept the payload that it will then take through the charging port interface and store directly into the EEPROM. And so now you have the ability to not only configure the application and deploy that into the field, but this will also offer the ability to provide updates in the field and enabling that flexibility that will provide some longevity to the overall solution. So we talked a bit about the configuration and the ability to configure this product using our graphical user interface. This graphical user interface can be leveraged in the cloud at dev.ti.com, as well as downloaded locally onto your desktop. But this GUI is really built in order to provide all of the mechanisms to configure, to download, and create those application configurations used in the customized product, as well as some monitoring capability that's built directly in that is really helpful in the context of doing that early development using the 772 or 762. As mentioned as well, we do have a reference design that is published that really talks to not only the EMI performance that is represented here, but also to just the physical design, the thermals, overall performance of the design and application. So this can be a useful reference point when you're building your own product and looking for some direction in terms of how to get the most out of that product design. So with that, this is my last slide. There's a number of items listed here. I think the takeaway is that if you look to ti.com and you search on TPS 25772-Q1 or 762-Q1, those searches should take you directly into the product folders on ti.com, where you'll find links to all of this additional information that's shown. So that be it the EVMs, evaluation boards for development, the access for the graphical user interface that I mentioned, which is directly accessible on the web, as well as the reference design and additional documentation focusing on our SPM, the firmware update capability, as well as how to use the GUI in the most efficient way in order to build your design. So with that, I want to thank you for your time, and hope you can get started, and looking forward to your development on the 772 and 762 products. Thank you.